Okay, evolution, part 1. We're going to be talking about the different evidences of evolution. Because keep in mind, when we talk about a theory, and we talk about the theory of evolution, we're not talking about just some guess. Okay, when we talk about evolution, the theory of evolution, a theory in science is something that has to be backed by a lot of evidence, okay, by experiments or by just lots of things that we see in nature. A theory is not a guess. In science, what a theory is we are taking the evidences that we have and trying to explain why we see that. Okay, so why do we see this diversity and yet at the same time this unity of life? Okay, so that's what we're going to talk about, some of the different evidences that we have for evolution. Okay, so just a little bit of evolution humor here. I mean, we talked about how evolution is not directional, and that's kind of what this picture here is making a joke about, how, you know, you go from being this awesome raptor with teeth and big old claws to this little tiny kiwi bird. That's what it looks like, that has a long beak and 2 little legs and little wings that can't even fly. Okay, so evolution isn't always making things bigger, better, and awesomer. They just are making things so that they can adapt to their environment. This is just plain silly humor, the lion on the stilts. And then this, hopefully a little bit of motivational. You are the result of 4 billion years of evolutionary success. Act like it. Okay, so speaking of time period, if you take a look at this chart, you'll see the present time up at the top, and the further you go down, the more in the past you go. Okay, so Cambrian is way, way, way long ago. What's important about this one that I want to point out are the extinctions. So in class we will be watching, or you will have already started, depending on what class you're in, you will already started the extinction video that I have for you guys. It talks about these 5 different extinctions, so we're not going to waste more time on them. Well, we'll talk a little bit more about them later. But, alright, first target we're going to hit is 9. Explain the evidence for evolution from other fields, including geographical. So we're going to be looking at geography and how that supports evolution, geological evidences, physical evidences, chemical evidences. Okay, so first, biogeography. Fossil records, we'll talk very briefly about biogeography. There's not a lot there that you need to know. Fossil records, extinctions, homologous structures, analogous structures, vestigial structures, DNA, embryology, and I think that's really it, all we're going to talk about right now. Embryology we'll get to when we get to that slide. Okay, so geography, you're studying the different continents, okay, and the countries and all that fun stuff. Okay, biogeography is we are taking a look at where life was across those continents, which is very interesting because the continents have not always been in the position they are now currently. And actually, the continents continue to move and drift. Okay, but that's a topic for another day. So if you take a look down here, we have this little fossil guy, fossil of the Cyananthus. Cyananthus was a Triassic land animal, which means he was not a swimmer. Okay, which is supported by this fact here that we find fossils of Cyananthus in South America, but we also find them in this region in Africa, which makes sense if the continents were the way they are shown in this picture. It would be impossible for this little land reptile to swim all the way across the ocean to get from where South America is now to where Africa is now. Okay, and yet we find fossils of these guys here, so we know that they had to have been there at one point. Okay, you know, it's the same story for each one of these. If you take a look at, there's plant evidence, there's evidence of different reptiles, of different animals that we find spread across these continents in a way that supports this arrangement of continents. Okay, so now we're going to talk about fossils, and as we're talking about fossils, we're actually going to hit target number 11 as well as target number 9. Okay, so fossil record. Most fossils are going to be found in sedimentary rock. And the first thing we're going to talk about is relative dating. Relative dating is pretty logical. It's like if you were baking a cake and you're doing multiple layers, you put the bottom layer down first, and then you put your cream or whatever you like to put in the middle of your cakes, and then you put that top layer on top. Okay, and then if you were to look at that time-wise, well, obviously you didn't put the top layer first and suspend it in nothing in air and then put the cream and then put the bottom layer down. You obviously put the bottom layer down first. Okay, so that's the same kind of concept here as we look at the different sedimentary layers of fossils. Okay, the deeper layers are the oldest layers because they were laid down first. So fossils that we find in those layers are going to be older, like here, this trilobite here, this fossil here is going to be older than a fossil we find here. Okay, because this fossil was in layer 1, which had to be laid down first, and then this one here. So it's just a little bit of a logic problem. Okay, deeper fossils mean older fossils. Okay, now we can also go through and we can date the rocks above and below the fossils to get a good idea of how old they are. Okay, so we can get relative dating. We can say this guy is much older than this guy here because of how many layers are in between them. Okay, that's relative dating. Then we can also go through and do radiometric dating. Radiometric dating, this is when we take an isotope. If you think way back to the beginning of the year when we learned about our chemistry, an isotope is an atom that has one or more, depends on which isotope you're looking at, neutrons. Okay, so carbon-14 is used most popularly because we know, well, think about when we learned about photosynthesis. Okay, what are the requirements for plants? They've got to have light, they've got to have carbon dioxide, and they've got to have water as well. Okay, carbon dioxide is absorbed, it's broken down, and we went through that whole process in photosynthesis of what happens with that carbon dioxide. But carbon is then absorbed into the different plants as well as the animals in all throughout history. Okay, we know about how long it takes for that isotope to break down, that carbon-14 to break down. Okay, a half-life, all it simply means is how long does it take for this isotope. Okay, if we take one plant and we can figure out how much isotope carbon-14 is in it, and how long does it take for half of that carbon-14 to be left in it. Okay, because an isotope is unstable and it's going to try to break down into a more stable, either a more stable isotope or break down into the atom that's not the isotope. Okay, it's going to try, it's unstable, it's going to break down. So we can measure how long it takes for that to break down, and however long it takes to go from this whole circle here to this half circle, or this whole amount of carbon-14. Okay, so we can take something and take a look at how much carbon-14 it has in it, and then we can watch it and measure how much carbon-14 it has in it. And once it has half the amount that it started with, then that's how we figure out our half-life. Carbon-14, is it like 5,000? Let me see if I have it written down somewhere here. Carbon-14 is like 5,700 years, something like that is the isotope. Okay, so it's a long time, which is what makes it predictable. Now down here we also have potassium 40. Carbon 14 for organic organisms is used a lot. There are, for inorganic things like rocks, we can use potassium 40. Its half-life is 1.25 billion years. Okay, so it takes a really long time. Right? So yeah, this picture here is a good, let me get my pen fixed. It's also a very good illustration, if you will. Okay, pen's not going to work. If you take a look at the mineral deposit, so most of the atoms are not radioactive. However, these little red stars, those are the radioactive. So you can go and count how many they are. Okay, once we have half the amount that we started with, once we have half that amount, that's 1 half-life. And then half of that half is going to be 2 half-lives. And then half of this half is going to be 3 half-lives. Okay, keep cutting it down by half. Alright, extinctions, species adapt to survive, or they go extinct. They're, out of all the species that we know of that we have on fossil, or that we have discovered, 99% are extinct. Okay, so there's lots of extinctions. Okay, extinction is a natural part of life. It's a natural part of evolution. It's important because it will go in and it'll actually open up other niches for other species. So this picture here is of a dodo bird, which if you've seen up, they have the little dodo bird that falls off the cliff and they're like last female and then they all die. Okay, so mass extinctions are much larger. Okay, a mass extinction is it's considered a mass extinction when at least 60%, so more than half of the population, is wiped out. There's rapid extinction of a large number of organisms, so we're looking at more than just the T-Rex or the Triceratops. Okay, we're looking at many different organisms where more than 60% are being wiped out. Okay, there are 5 of these, and the video goes over 3, 4, 5. There are your 5 mass extinctions. If you'd like to know more about the extinctions, this website that I've put in there is really great. It's really cool. I would highly suggest you go take a look at it if you're interested. Okay, and all you have to do is go type in NHM extinctions, mass extinctions. Background extinctions, these are smaller, not nearly as extreme as the mass extinctions. Okay, then there's homologous versus analogous extinction, or not extinction, sorry, we've moved on. Homologous versus analogous structures. So a homologous structure is when we have similar structures that develop because of a common ancestor. Whereas analogous structures, these are structures that are similar, but are structurally unrelated. Okay, so I've got a couple on here. I've got better pictures here. Okay, so something like the dorsal fin between the shark and the dolphin. Sharks are fish, dolphins, mammals. They do not come from a common ancestor. However, at least not too closely. Okay, but if you take a look at the dorsal fin, it's very similar. Those would be an analogous structure. Okay, same thing with the shape of the body, the flippers and the pectoral fins. Okay, bats and birds do not come from the same ancestors. Birds come from reptiles, from dinosaurs. Okay, and bats actually come from mammalian. However, you can see they both have wings that allow them to fly, and similar in structure as well. Okay, vestigial structures. If you take a look, these are things that are fully developed but are not functional. Okay, like in humans, we have our appendix. In the snake here, we've got little legs, little leg bones. There's a pelvis here from the dolphin. The dolphin doesn't walk, so it still has that kind of that remnant left behind. Okay, and then embryology. Embryology, this is where we're going to end up. This is no matter what you are, if you're a fish or a bird or a pig, the beginning stages are very similar of the embryo.